we have talked about de Moivre's product theorem, quotient theorem, and power theorem. And it's time to roll out the final bit of this, the root theorem, or how to find square roots, cube roots, fourth roots, and so on. And this video is going to be rather introductory, and I'm going to walk through steps fairly slowly using this problem from the homework. If you are mostly okay with the root theorem, this might not be the video for you. Maybe skip ahead to the next video where I go into a little more introductory topic, intermediate topic. So first I want to talk about where this theorem, this beast, even comes from. If you think about what a power is, actually let's just go over the power theorem. I think that would be handy. If I write this in polar form, this complex number, it's going to be the following. You'll recognize this, hopefully. I have the modulus of z right here. That's like its magnitude, its bigness. And then these components right here, the theta, the cosine, the sine, those really have to do with the direction of the vector in the complex plane. So if I imagine taking this to a power, here's what the power theorem says. Take this to a power, and here's what you get. You get, first of all, the modulus raised to that power, and you get cosine of n times theta plus sine of n times theta. Those are little angles right there. Well, they're bigger than they used to be, but now if you accept this idea of the product theorem, all I want to do now is change n to be a fraction. So let's call it 1 over n. Okay, so that's just going to be z modulus to the power of 1 over n times cosine of, well, this time we have theta over n plus I sine theta over n. See, all I did was I flipped n around, so now it's a fraction. Well, you remember what this means, right? That means like square root or cube root or fourth root, whatever n is, it's that root. So this is where the root theorem comes from. And this idea over here of dividing theta by n, well, that's all this is. See, I'm just dividing theta by n, and the only slight complicating factor is this plus 2 pi k. And we'll talk about that more going forward. But this is the general idea. All I'm doing to get the root theorem is saying, let's pretend the power from the power theorem is now a fraction. And that's where roots come from. Okay, so let's get into this particular problem. The modulus of z is found in the following way. You take the square root of the real part squared plus the imaginary part squared, right? So for this problem, that turns into the square root of, well, the real part is -3/2. Okay, so we would put that there. And the imaginary part, a little more complicated, 3 radical 3 over 2 squared. So once the dust settles from this thing, you're going to find that the modulus is equal to 3 once you work through those algebras. Theta is found in a different way. We use a different formula for theta. That is the tangent one. So we would say theta equals the inverse tangent or the arctangent of the imaginary part over the real part. So for this particular problem, once you do the math, skipping ahead a little bit, that's going to become the inverse tangent of, let's see, looks like negative radical 3. And now it's just time to think about the unit circle and say, where are my tangents equal to radical 3's? A negative radical 3's. Here's an option, and here's an option. Those are your negative radical 3's for tangent. Well, which one's appropriate? If you look at this in its rectangular form, you'll see that's negative x positive y. Okay, that's quadrant 2. That points to this point right here. So I would say, oh, that's just 2 pi over 3. Okay, that's the preliminary stuff just to get us started. Now, we're getting into how to use the root theorem for square roots in particular. I'm only going over square roots in this problem. So what we do is we change n in this formula to 2. And what that means is the second root or the square root. So take this big old formula, change all the n's to 2's right here, here, and here. And that's where we came up with these things. And now what I want you to do is use the r and the theta from the previous step. I'm talking about these guys right here. Okay, so use those moduli and angles, the modulus and angles from the previous step, We're going to substitute those in and see what we get. This becomes the square root. Previous modulus was 3, so I'm putting that right here. Times the cosine of, now, first thing I'm going to do is use k equals 0. That's important. See right here, w sub k, that's going to be 0. So this becomes theta over 2. Now, theta is 2 pi over 3, so this is 1 pi over 3. And that's it for the first root. The hard part really is finding the angle. Now, the next thing you do is you plug in k equals 1 for the second root. Okay, so what happens when k equals 1? Well, you get an extra plus 2 pi up here. And eventually, that 2 pi will be divided by 2. See this part? It's going to be plus 2 pi divided by 2. So it's really just plus pi. And now what's pi over 3 plus pi? Well, 4 pi over 3. So that's your angle for the second root. The modulus of the second root stays the same as the first root. Okay, that's still square root of 3. So that's our polar form, and we've converted things from polar form to rectangular form a ton. I will just do a quick example of that, and you can do the rest of it on your own. What this becomes is square root of 3 times, well, what's the cosine of pi over 3? That is 1/2. And what's the sine of pi over 3? That's going to be radical 3 over 2. Now, we still have to multiply these by radical 3, distribute that, make it look a little more pretty, so it's in rectangular form, which is just a plus bi like this. But I think we're most of the way there. Now, one more point about this angle part, and I think this is, if there is a hard part to this particular idea, this root theorem, this is it right here, finding those angles. And I want to point something out. If you look at a unit circle, where was our original number? It was, what was it? 2 pi over 3. Great. Our original number was like here. Okay, that's our original. Now the roots, I'm sorry, that should not imply a unit circle right there. Okay. So this is at radical 3 and 2 pi over 3. Our roots were shorter, right? We square rooted 3, but the angle was also different. Look, here was the first angle. See, that was the first root. And to find the second root, remember how I added pi? Well, look at the symmetry that comes up here. Isn't that nice? It's just 180 degrees around, or pi. And then if you go another 180 degrees around, like this, you get back to the beginning. That's why there's only 2 square roots, according to this theorem.